Today I'm going to be completing Part D of Homework 1 for separations. In Part D, we are going to derive the relationships between the vapor and liquid components of an ideal binary mixture of constant relative volatility. So I'm going to get started with a couple variables that we're already familiar with, like the partition coefficient, which I'm just going to label PC here, which says AI equals yi over xi. We're also going to need the equation for relative volatility, if you couldn't guess from the problem. Just ki over kj. And last but not least, we're going to need to remember the principle that y2 is going to equal 1 minus y1, and x2 is going to equal 1 minus x. Alright. So to get started here, we know that y1 equals x1 times k1. We also know that y2 equals x2 times k2. But what we can do with this is we can sub in our 1 minus y1 and our 1 minus x1. So we can say that 1 minus y1 equals 1 minus x1 times k2. Now, if we divide these two expressions by each other, we get total expression y1 over 1 minus y1 equals x1 over 1 minus x1 times k1 over k2. Of course, k1 over k2 looks familiar because that is our relative volatility for components 1 and 2. So, let's go ahead and sub that out. Move over to here. We can say that y1 over 1 minus y1 equals alpha 1, 2 times x1 over 1 minus x1. Furthermore, we can move this variable to the other side, which will give us y1 equals alpha 1, 2 x1 times 1 minus y1 all divided by 1 minus x1. And if we distribute our alpha element, we get y1 equals alpha 1, 2 x1 minus alpha 1, 2 x1 y1 all over 1 minus x1. Now again, we're going to distribute this out to this side. I'm being very careful here, not taking any chances, as I've heard some scary things about this algebra here. It's going to give us y1 minus y1 x1 equals alpha x1 minus alpha x1 y1. Now, moving back over here again, if we isolate our y1, we get y1 times 1 minus x1 plus alpha x1 equals alpha x1. And finally, we move this entire expression over to under here, we can get y1 equals alpha x1 over 1 minus x1 plus alpha x1. And this here is our relationship between the vapor and liquid components for a binary mixture with constant relative volatility. And you can see that having this constant relative volatility definitely helps to make certain separation processes much more trivial. So now, why don't we go check out how this looks practically over in Code.
All right, moving into the Python segment of our coding, I've written out our objectives here. So we need to create arrays of x1 and y1 that exclude the endpoints 0 and 1 to avoid a division by 0. And to start out doing that, we're just going to have x1 equal numpy.array. And we're just going to take our x1s and go from 1 to -1, as that will take off both the first value in our x1s, which should be 0, and the last value, because the endpoints will result in a division by 0. So that fixes that. Let's just check x1, make sure it's all good. We're going to do y1 is also just going to be the exact same thing. It's going to be numpy.array y1s going from 1 to -1. And that finishes out our first part. So we've avoided our division by 0. We've excluded our endpoints. So now we want to put in that average volatility that we were talking about. So I'm going to say AVG for average is going to equal, yeah, exactly that. I will just copy and paste it from up here. And this value here is going to be our volatility, or our relative volatility, which is going to stay constant in this problem. Moving on from this, now we want to make our figure. To our figure, we're going to add all of our previous data along with our equation that we just derived on the whiteboard. And we're going to compare and see how these two different ways of plotting compare. So I'm just going to do our usual stuff. I'm going to pull from up here our average line that we made earlier, as well as our markers that we also made earlier, our markers that we derived from up here above. And now comes the part that's different. So I'm going to do fig.add scatter. And x is going to stay as just x1, but y, we're going to go off of our equation we derived up here on the whiteboard. So if you remember, it's going to be our average relative volatility, our AVG, times our X1, all divided by 1 minus X1 plus our average times our X1. And then we're going to have this be mode equal lines. From here, I'm actually going to give these some proper names. So I'm just going to name this average basic line. That'll work. I'm going to name this our C5 scatter. And finally, I'm going to name this our average volatility line. And finally, going on from here, all I'm going to do is exactly as the AI says, update our layout to our usual stuff. And let's just see how this looks. All right, what's happening here? Forgot to put in our name. All good. Fantastic. So you can see here that our average volatility line derived up here appears to fit this line. Our original markers we figured out from all this stuff up here very well. Aside from, of course, the excluded endpoints, they seem to match perfectly. I'm actually going to widen out this plot a little bit more so we can see it just a tad better. Look at that, yeah. This line is essentially right on the money, which means that benzene and toluene are likely a very close to ideal binary mixture that have constant relative volatility, being that these lines match so well. And I think that finishes part D of homework 1 for separations.